Okay, today we're going to talk about measures of spread or variability. And what that means is when you measure a bunch of different things or the same thing over and over again, the numbers aren't all going to be the same. Even if you measure the same thing over and over again, you're likely to get slightly different measurements each time. So the numbers that you collect are going to be spread out, maybe a little tiny bit, or maybe spread out a lot, okay? And we're going to talk about ways to measure how much are the numbers spread out from each other. The previous lecture was ways of measuring the center of your data. And today we're going to talk about ways of measuring how much is the data spread out. Okay, so the first thing that I want to do is give us an example. Okay, so suppose we are interested in studying the question, how fast can an adult run 50 meters? Okay. Now, when you measure these things, the amount of time it takes an adult to run 50 meters, there's going to be variability in the measurements. And I want to go over with you 4 types of variability. Let me ask you a question before we get started with this. What's the population here? The population is adults, right? Can I measure how fast they can all run 50 meters? Well, theoretically I can, but not realistically, right? It would take me decades. There's too many adults in the world for me to travel around and have them all run 50 meters while I time them. So what would I do? I would take a sample of, let's say, 20 adults. Let's not argue about whether or not that's enough, okay? And we'll do that later. Let's just say that that's what I'm going to do. And probably I would take a whole bunch of samples, okay? So the population is all of the adults in the world, and I would take a sample and ask those people to run while I time them, and then I would probably take another sample and ask those people to run, and so on and so on. So when I do that, there's going to be variation in my measurements, okay? And there's 4 types. One is measurement variability. And that has to do with variability in the actual way of measuring. Okay, so I can give you a couple of examples of measurement variability. One example would be, suppose I take a sample of 20 people, and then I have, one of those fake starting guns like they use in the Olympics, right? In one hand, and in the other hand, I'm holding a stopwatch. And when I fire off the starting gun, I start the stopwatch. And then when the person crosses the finish line, I stop the stopwatch. Well, that is partially dependent upon my reflexes, right? When they cross the finish line, how quickly do I move my thumb to press the button on the stopwatch? And for one person, I might stop the stopwatch at the exact instant that they cross the finish line. And for another person, even though I'm trying to be consistent, for another person, I might have moved my thumb slightly slower and stopped the stopwatch 1/100th of a second after they cross the finish line. So then there's going to be some variability there that's built in that is based upon the fact of how good am I at starting and stopping the stopwatch accurately. Another example of measurement variability would be if I take a sample of 20 people and I time them, and then a coworker of mine takes a sample of 20 people to the other side of the track and they time those 20 people. We have each a stopwatch, and one stopwatch might be slightly more accurate than the other. So there's going to be variability in our two measurements based upon the fact that we're using two different stopwatches. Okay, so that's called measurement variability. Another type of variability is natural variability, and this is a variability that just happens on its own. If I take 20 people and I time them while they're running, some people are going to be faster than others. And so there's going to be variability in the times that I get. That one's pretty simple to understand. 3 is called induced variability, which would be where you specifically do something to cause variability. Like I might let my sample wear running shoes, and then my coworker tells his or her sample that they have to run barefoot. So that's going to cause differences in the times, and it's going to create more variability. Okay, why would they make them run barefoot? I don't know. I don't think that would be a good idea, and that's not the point. The point I'm trying to make is just that if you do something like that and it causes variability, that kind of variability is called induced variability. Okay? And number 4 is called sample variability, which is similar to natural variability, but a little bit different. Sample variability would be where I take a random sample of 20 people, my coworker takes a random sample of 20 people, and just by happenstance, I might have ended up with 20 fast people, and they might have ended up with 20 out of shape people, which means that my sample is going to be inherently different than their sample. Okay, as a whole. I'm not talking about each individual being different. That would be natural variability. I'm talking about the samples as a whole being different than each other. That's called sample variability. Okay, so you should know those words. I'm really going to be more concerned about you calculating variability, but you should still know those words, that those are the 4 different types. Okay, so now how do you calculate variability? How do you put a measurement on it? If you look at a set of numbers, what is going to dictate you looking at those numbers and saying, oh, those numbers are all pretty similar? That would mean not very much variability. Or what if you look at the numbers and you say, geez, those numbers are all over the chart? Then that would be a lot of variability. What we need to discuss is, how would you make that judgment of these numbers are close together and those numbers are spread way out? Okay, what does close together mean and what does spread out mean? So here's what we're going to do. I'm going to write down 20 numbers, and let's pretend that these are how fast 20 adults ran 50 meters. Okay, so suppose we sample adults, okay, and time them. In seconds. Whoops. My pen is not working here, so I'm going to finish this sentence. Okay, I can't even finish the sentence. Okay, I'm going to try to fix my pen here. Okay, I think this is going to work better now. So suppose we sample 20 adults and time them in seconds, and we get these numbers. One person was 9 seconds, a couple of 9.5s, four tens, four 10.5s, six 11s, and three 11.5s. So those are the 20 times that we recorded. Okay? And we want to talk about putting some sort of a number on this that will give us an idea of how far it's spread out. Okay, now, of course, you could say, well, they're spread out over a distance of 2.5 seconds. The slowest one's 9 and the fastest one's 11.5. And certainly that's one way of doing it. Another thing you can use to measure if they're spread out a lot is the interquartile range, which we talked about a few lectures ago. But a more common idea is to try to get an idea, not just the spread, like the distance from the smallest to largest or something like that, but we would like to talk about how far are these numbers away from the average. Okay, so what we're going to do first, the first thing we're going to do is we're going to find the average. Okay, now this is a sample. I want you to remember this because this is very important. I want you to remember the symbol that we use for the sample mean. Remember, it's X bar. Okay? So we're going to add up all of the numbers. So there's a 9, and there's two 9.5s, and there's four 10s, and four 10.5s, and six 11s, and three 11.5s. And that makes up the 20 numbers. Okay, and what we come out with from that is 10.525. That's our sample mean. Okay? So, let's find how far away are the numbers from the mean. Okay? So what that means is we are going to add up. Now, this might not be our final decision of what to do. I'm just giving you some ideas, okay? We can add up. Remember, capital sigma means add up. And we're going to take each data point and subtract the average. And we're going to do that for all data points. So I just want to remind you that this would be x1, this would be x2, this would be x3, and so on. So I put down here x sub I, and then I say I goes from 1 to 20. Okay, so that means 9 minus 10.525 plus 9.5 minus 10.525. And then there's another one of those. So rather than writing another one, let's just say times 2. Okay, and then plus 10 minus 10.525. And there's actually 4 of those rather than writing it 4 times. Let's just write times 4. Okay, plus, and then we have 10.5 minus 10.525, and how many of those are there? There's 4 of those. Plus 11 minus 10.525. There's 6 of those. Plus 11.5 minus 10.525. And there's 3 of those. This is one idea, okay? We're measuring the distance from each data point to the average. And then we're adding all those distances up. What I would like to do actually is find the average distance. Okay, but let's just take one step at a time. All right, now I'll go ahead and tell you what this equals. Let me work it out. Okay, so that comes out 0. Well, that's not very informative, is it? Why did it come out to equal 0? Well, I'll tell you why. Because some of these numbers are negatives, like here. 9 minus 10.525 is negative. There's negative, there's negative, that's negative, and these are positives, and what's happening is the positives and negatives are canceling each other out perfectly, and so we get 0. Okay, so that's a problem. That's not going to be of any use to us. That makes it look like there's no variability at all, right? So what we need to do is we need to prevent the positives and negatives from canceling out. And the way to do that is to make sure that there's no negatives. Let's make it so that everything's positive so that there won't be any canceling out. Okay, what's one way of making sure that the numbers you're looking at are always positive? A nice little trick for doing that is to square them. Okay, these things here are all called deviations. Okay, and the problem is that if you add up all the deviations, they will cancel out every single time and give you a sum of 0. So instead of adding up the deviations, what we do is we add up the deviations squared. And what that does is that makes everything positive. so the different ones can't cancel each other out. Okay, now if I calculate this, let's see what I get. Okay, that gives us 9.7375. Okay, so this is called the sum of the squared deviations okay, and why did I square them? So that the negative ones would become positive, so they wouldn't cancel out with the ones that were already positive. Okay, but that squaring creates a little bit of a problem that we're going to have to get around in a minute. But let's not worry about that yet. What we want to do now is we would actually like to find the average of the squared deviations. So what does average mean? You add them up, which we already did. We added up the squared deviations. Now I would like to divide that by how many there are, which is 20. Okay? So we're going to do this. The sum of the deviations squared, and we're going to divide that by 20, and we get 9.7375 divided by 20, which equals 0.486875. Okay, that is the average of the squared deviations. And that has a name. That's called the variance. That's an important thing. Okay? So that gives us an idea of how far the average person's time is away from the average time. Okay? But now let's go back and deal with that problem. When I squared all the numbers, which I did in order to make them positive, so the positives and negatives won't cancel out, another thing that did was it made the numbers a different size, right? When you square something, not only does it make it positive, but it actually makes it a different size. I would like to try to counteract that size change as best I can. So what we're going to do is we are going to take the square root of that whole thing. So that would be the square root of 0.48685, and that equals 0.69. I'm going to write out a lot of decimal places. Not that you would necessarily need this many, but I'm going to write them down anyways. 0.6977642 86848. Okay, so that is the square root of the average of the squared deviations okay, which is the square root of the variance. Which is also called the standard deviation. Okay? So I'm going to shrink this down so we can see back here. So we measured those we measured those 20 times up there at the top. We measured these 20 times. And we got a standard deviation of, let's just round that off when I'm talking. I'll leave it written the way it is, but when I'm speaking, I'll just round that off and say the standard deviation is about 0.7. Okay? Now, is that a lot or a little? I mean, that's an opinion. That's up for you to decide if you think that's big or small. What's important is this. If your friend takes a sample of 20 people and they time those 20 people and they get a standard deviation of 0.8, what that tells you is that their sample is spread out more than yours. It has a higher variance and a higher standard deviation, so it has more spread. And if another friend times 20 people and their times have a standard deviation of 0.5, then that tells you that that sample is more closely grouped together. Okay? So to just measure the standard deviation of a sample is kind of neither here nor there. It just is what it is. The important thing is you use the standard deviation of different samples to compare the two samples and see if one sample is more spread out than another. Okay? Now I'm going to write down some formulas because we're starting to get now into a lot of formulas, and you're going to need to know these. There's no getting around it. If you want to do well in this class, you're going to need to know these formulas and the names. Okay? So remember, you have a population, which is what you would really like to know about, but is probably too big to actually study in person. So instead you do samples. Maybe one sample, maybe a whole bunch of samples. Okay? So, what have we covered so far? We've covered the mean, which means you add up. In theory, we don't actually do this because the population is too big, but theoretically, it would mean that we add up all of the, we don't need a parenthesis here really, but I'm going to keep it, oh actually we do need a parenthesis. We add up all of the data numbers and then divide that. I guess we don't need parentheses actually, not for this one. We divide that by the size of the population, which we're going to use capital N. Okay, let me write that down, that capital N is the size of the population. And we'll use little n for the size of your sample that you do take. Okay, Now you should know some algebra, and when you look at that, you should know that we can rewrite that like this, which most people prefer to put sigma x over n. Okay? So that's the population mean. You need to know what we call that. What do we call the population mean? We call it mu. And you need to know that, okay? All right. For the sample, you take the sum of all of the data points and divide it by the sample size, and that's your sample mean. And what do we call the sample mean? You need to know that. It's x bar. Okay? So that's how you calculate the population mean and the sample mean. I'm going to write here, I'm going to write the word mean over here, okay? All right, so we learned that in the previous lecture. Now, what are we learning in this lecture? We're learning the variance. We learned how to do that. So what did we do for variance? You add up the squared deviations which means each data point minus the mean, that's the deviation, and then you square that. And then we take the average of, so that means we divide that by the population size. And that's called the population variance. Okay? For the sample variance, it would look the same, except a couple of small differences. It would be, instead of mu, it would be x bar. And this would be the sample size instead of the population size. And I'm actually going to change that number in a minute, but I don't want to yet. Okay? So that's how you do variance. And then there is standard deviation. Okay, which is the square root of the variance. Okay, now for the standard deviation of the population, we use the Greek letter sigma. And for the standard deviation of the sample, we use the English letter S. Which means, by the way, that the variance of the population would be called sigma squared, and the variance of the sample would be called S squared. Okay? Now, one last thing. And I didn't explain this sooner because I didn't want it to confuse you, because these formulas can be confusing enough. There's so many formulas all of a sudden. But when you do the standard deviation of the sample, you do one more thing, which is kind of considered just a fudge factor a little bit. And that is, do you remember why this n is down there? It's because we were finding the average of these, right? Okay, so statisticians built into this an extra little fudge factor, which is instead of dividing by n, they divide by a number 1 smaller than n. I don't want you to stress about why that is right now. Okay, I just want you to remember that that's what the formula is. That's just an extra fudge factor is all it is. Okay? Personally, I would rather that it's not like that. I think it would be simpler to understand if it was just n, but that's the way statisticians do it. Okay? I'm going to organize these in a nice table. Okay, and you're going to need to know these 6 formulas. There's just no getting around that. Okay? That's something you're going to need to try to get down. All right, and then one last thing to cover today is this. Suppose you look back at our original list of numbers of the 20 people that we timed. Let's just scroll up and look at that list again. I'm going to zoom in on this. Okay, now, let's say, I'm just going to pick one of these people. Let's say this person right there that ran it in 9 seconds. You would say, wow, he's the fastest one of the group, or she is the fastest one of the group, right? But you would kind of like to have an idea of, remember what the mean is. I just want to write that down for you again. Remember the mean was 10.525 seconds. Okay? So that person ran 50 meters in a time that's shorter than the mean. So they ran it faster than the average. But we want to have some sort of an idea of, is that surprisingly fast or is it just a little fast? Like, surely if somebody could run 50 meters in 3 seconds, you would say, wow, that is absolutely amazing. Because 3 seconds is way faster than the average of 10.525, right? For somebody to run it in 9 seconds, that's a little bit faster than the average, and we would like to have an idea of, is that surprising or is it just a little bit interesting? Okay? Do you want to sign this person up for the Olympics, or do you just want to say, oh, you're a little bit faster than everybody else? So we need some sort of a measurement. And what you do is you use the standard deviation as kind of like your main measurement of spread. And you ask yourself the question, how many standard deviations away from the average is that data point? Okay? Let me write this down. To see if 9 is a surprisingly small number, we ask, how many standard deviations, I'm just going to abbreviate, okay? How many standard deviations is 9 away from the average? Let's use the word mean instead of average. That's the question we ask. Okay? In other words, we're asking the question, 9 minus the mean equals how many standard deviations? So it equals the standard deviation times what? That's what we're asking. Okay? How do I find question mark? Well, I just do a tiny bit of algebra. I divide both sides by s, and those would cancel out, and I get question mark equals 9 minus 10.525 divided by the standard deviation. Okay? Of course, question mark is not really a variable. So let's choose a letter for that instead. And statisticians use the letter Z. And that's called the Z-score. Okay? Now remember, our standard deviation for this example was about 0.7. So let's calculate the Z-score. So we get 9 minus 10.525 divided by 0.7. And you come up with negative 2. I'm going to round off to 2 decimal places here. 2.18. So what that tells you is the person who can run 50 meters in 9 seconds is a little bit more than 2 standard deviations below the mean. Okay? So that's our conclusion. This data point is slightly more than 2 standard deviations below the mean. And that is surprising. Okay? To be that far faster than the average is surprising. That would put them in probably about the top 2.5%. Okay? Anything more than 2 standard deviations away from the mean is usually considered to be something that you would definitely take note of. Okay? All right, so we have a new formula called the Z-score, which is the data point minus the average divided by the standard deviation. Let's put that in our table of formulas that we're learning today. When you're looking at somebody in the sample, you calculate their Z-score by taking their data point, subtracting the sample mean, and dividing by the standard deviation. Okay? If it were possible to measure the whole entire population, then you would do, for a Z-score, you would do one of the data points minus the population mean divided by the population standard deviation. And that's called a Z-score. And that's a way of measuring how far away is each individual data point from the average. It tells you how many standard deviations is that from the average. Okay, this is a lot of information here. And you're going to need to put in some effort to knowing those 8 formulas. Okay? And that's the end of chapter 2. And that's all for this lecture.